Good afternoon. During the last class, I proved that the derivative of an invertible function is an invertible matrix. Today, I will present a result from analysis known as the inverse function theorems, which is essentially the converse of the previous result. So we have the following theorem. Which says that if f from Rn to Rn is smooth on a neighborhood of P in Rn and dfp is an invertible linear transformation, then there exists a neighborhood U of P such that V equal f of u is a neighborhood of f of P, and f seen as a function defined on U with values in V is invertible with smooth inverse. So the hypotheses of this theorem are the following. We have a smooth function on a neighborhood of a point, and the derivative df at p must be invertible. Then there exists a neighborhood u of p, possibly smaller than this one, and such that the function f, seen as a function defined on u with values in f of u, then is invertible, and this inverse is smooth. The reason why this result is remarkable is that you can get the smoothness of the inverse function and the existence of the inverse function just from the fact that this map here is invertible. I want to show you a simple example. consider the function f defined in R2 with values in R2 defined by this formula f of x of y equal x squared plus y x y. This function is clearly smooth because its component function are smooth. Let's call them f1 and f2. Let's fix P be the point of coordinate xy in R2, and let's compute the derivative df at P. So we have by definition that dfp is a matrix given by df1 dx at P, df1 dy at P, df2 dx at P, df2 dy at P. Simple computation shows that this matrix is 2x, 1, y, x. So if we choose P to be the point of coordinates 1, 1, then df at 1, 1 is 2, 1, 1, 1. The determinant of this matrix is invertible, so determinant different from 0 implies df 1, 1 is invertible. Then the inverse function theorem implies that the restriction of f to a small neighborhood of 1, 1 is invertible with smooth inverse this result could have been verified making the computations. What do I mean? I mean that we could check without using the theorem. How can we do this? We look at the formula for the function, and we try to find an inverse solving the system a equal x squared plus y, b equal x y, so solve it for x and y. Near x equal 1, y equal 1. It is clear that this would require more effort than using our theorem. Okay, the next notion I need is the characterization of smoothness for functions whose domains are not open. So we have the following definition. If X contained in Rm is a set not necessarily open, then the function f defined on X with values in Rn is said to be smooth if for all p in X there exists a neighborhood U of P in Rm and a smooth function f tilde to find on this neighborhood with values in Rn that agrees with f on the intersection x intersection u. So essentially this definition says a function f defined on a set is smooth if there exists for each point p a neighborhood u and an extension of f known as denoted by f tilde, which agrees with f on the intersection x intersected with the neighborhood u. Now we are ready to present the definition of diffeomorphism and diffeomorphic sets. So definition: 3.13 x contained in R M1 and y contained in R M2 are called diffeomorphic if there exists a smooth bijective function f defined on x with values in y, whose inverse is also smooth. Such a function is called diffeomorphism. Let's see some examples. So let's consider the sphere S2 that is a set of points of R3 such that x squared plus y squared plus z squared is equal to 1, and the ellipsoid E that is a set of points of R3 such that x over a squared plus y over a over b squared plus z over c squared equal 1, where a, b, c are real numbers which are positive. These two sets of R3 are diffeomorphic So S2 and E are diffeomorphic. For every choice of A, B, C positive. What is the diffeomorphism here? So consider the function f from S2 with values in E, which is given by f of x, y, z equal to ax plus by, ax, by, cz. This map is clearly a diffeomorphism, Why? Because it is smooth, because it extends to the smooth function the smooth function on R3 defined by the same formula. Its inverse is easy to find, so its inverse is given by f inverse of x, y, z equal to x over a, y over b, z over c, which is smooth for the same reason. One more example. So the plane R2 is diffeomorphic to the paraboloid P x y z in R3 such that z is equal to x squared plus y squared. What is the diffeomorphism here? Is a sigma from R2 with values in P, defined by the formula sigma xy equal xy x squared plus y squared. The inverse, okay, this map is clearly smooth, and its inverse is sigma inverse from P in R2 and it is given by this formula sigma inverse of x, y, z equal to xy. This is smooth because it extends to the smooth function from R3 to R2 with the same formula. Okay, one more example. The upper hemisphere and the unit disk are diffeomorphic. The upper hemisphere is denoted by S2 plus, and it is the set of points of coordinates x, y, z in R3 such that x squared plus y squared plus z squared is equal to 1 and z is positive. And the unit disk denoted by D2 is the set of points of coordinate x and y in R2 such that x squared plus y squared is strictly smaller than 1. Okay, the diffeomorphism sigma between D2 and S2 plus is given by this formula, sigma x y. This is equal to x y square root of 1 minus x square minus y square. This is a smooth function on D2. The inverse sigma inverse from S2 plus with values in D2 is given by this formula, sigma inverse of x, y, z equal to xy. This is smooth because it extends to the smooth function from R3 to R2, defined by the same formula, defined by the same formula. Please observe that the inverse of this map is exactly the same as the one we presented in the previous example. It's not a case, it's not a coincidence. In fact, the last two examples are special cases of the following general rule that I present in the form of a lemma. So lemma 3.17. So if U contained in R2 is open and F defined on U with values in R is smooth, then its graph G, that is a set of points of the form x, y, f of x, y. Sorry, I have to write something else. With the x, y in U is diffeomorphic to U via the diffeomorphism sigma from U to G, defined by sigma of xy equal xy f of xy. So in other terms, the graph of a smooth function, this is a graph of the smooth function f, is diffeomorphic to its domain, which is an open set of R2. Okay, now we start the study of the surfaces. In order to do this, I need two preliminary notions. The first one is the notion of open set containing another set, and the second one is the notion of neighborhood. So definition, (3.18). So let S contain in Rn be a subset a set V contained in S is called open in S if V is the intersection with S of an open set in Rn. So this is the first definition. The second one, if P is a point in S, then a neighborhood of P in S is a subset of S that is open in S, and I just gave the definition of this, is it here? And that contains P. We are now ready to give the definition of regular surface. So definition, (3.19). A set S in R3 is called regular surface if each of its points has a neighborhood in S that is diffeomorphic to an open set in R2. So this definition says that a regular surface locally looks like an open set of R2. That is, for every P in S, there exists a neighborhood V of P in S, an open set U containing R2, and diffeomorphism sigma defined on U with values in V. Such diffeomorphism has a name is called a surface patch or a coordinate chart. It's not finished because I have to present the notion of atlas. So a collection of surface patches that together cover all of the points of S is called an atlas for S. Okay, let's try to make a picture to clarify what I wrote. So let's suppose that we want to check that this object is a surface. Then for each point P in the subset S over 3, there exists a neighborhood V an open set U in R2 and a map sigma, which is a diffeomorphism which send U on 2V. It is possible to give definition of surface without the adjective regular, and this is obtained replacing the word diffeomorphism with the word homeomorphism. So in this case, we would have maps which are continuous with inverse which are only continuous. Instead, in the definition of regular surface, we are asking for more. We want all the maps to be smooth with the smooth inverse. Okay, now let's prove a simple result which says the following. It says that the regularity of the surface implies the fact that the derivative d sigma q, where sigma is a surface patch, has rank 2. So let me write the precise statement. So we have proposition 3.21, which says the following: if S is a regular surface and sigma is a surface patch, then for all Q in U, the linear transformation d sigma Q from R2 into R3 has rank 2. How to prove this result? The proof of this result uses a technique we already used for proving that the derivative of an invertible function is invertible. So let's see the proof. Set P equals sigma Q. Consider sigma inverse to be extended to a smooth function on a neighborhood of P in R3. We denote by sigma inverse this extension. So we use the same notation. Then we can use the chain rule. And we have the derivative of sigma inverse composed with sigma at Q. This is equal to the derivative of sigma inverse composed with the derivative of sigma inverse at P composed with the derivative of sigma at P at Q, and the reason why we need to extend the function this way is that in order to give to be sure that this derivative makes sense, we need to work on an open set. Okay, this map here is clearly the identity. So this derivative here is also the identity. So this composition here must be the identity. So implies the sigma inverse evaluated at P composed with the sigma evaluated at Q is the identity linear map on R2. And this map is then a map of rank 2. Now, this is a composition of two maps having rank 2, and you know very well that the rank of a composition is less than or equal to the rank of the first map of the composition. So this implies that the rank of the sigma q is 2. And the proof is finished. Let's see now what are the consequences of this fact. The image of the sigma q is two-dimensional. It is spanned by the sigma q E1 and the sigma q E2, where E1 is a vector of components 1, 0, and E2 equals 0, 1 form an orthonormal basis of R2. This sentence means the sigma q E1, the sigma q E2 are linearly independent. Let's try to be more explicit. So suppose that the coordinate variables on R2 are UV. This implies that if sigma defined on U with values in V contained in S is our surface patch, then sigma is given by the following formula. Sigma of u v, this is given by x of u v, y of u v, z of u v. What is d sigma q? D sigma q is a matrix dx du at q, dx dv at q, dy du at q, dy dv at q, dz dvu at q, dz dv at q, and you see that the column of this matrix are exactly the partial derivatives of sigma with respect to u and v. So this is sigma u q and this is sigma v q. And we have seen in one of the previous lectures that sigma u q is exactly the directional derivative d sigma qe1, and the partial derivative of sigma with respect to v is the directional derivative d sigma q e2, and we know from what we observed before that these two vectors are linearly independent. We have also observed that these directional derivatives can be computed as follows. D sigma q e1, this is sigma composed gamma 1 prime at 0, where gamma 1t is a curve passing by q with initial velocity given by e1. So for example, q plus t e1. Now if we try to write down this formula using the component notation, this is equal to u0 plus t comma v0 if we assume that q is the point of components u0, v0. In the same way, d sigma q e2 is the directional derivative that we can compute by the following formula: sigma composed with gamma 2 prime at 0, where gamma 2t is a q plus t e2 that can be written as u0 comma v0 plus t. The variables u and v are called local coordinates. Now let's start to see a few examples. The first one is almost trivial. This is a plane. So every open set u over 2 is a regular surface covered by a single surface patch the identity function from u to u. So this is the proof of the fact that the plane is a surface. Please observe that we are implicitly regarding R2 as the xy plane in R3, and the reason of this is that according to the definition we gave, only subset of R3 can be regular surfaces. The next example is the cylinder. So let's show that the cylinder C given by the set of points of R3 such that x squared plus y squared equal 1 is a regular surface. How to prove it? Okay, let's consider every point P of coordinates x, y, z in C with x different from -1. This set here lies in the image of the smooth function sigma defined on minus pi times r with values in C. This is our open set U, defined by the following formula. Sigma of UV, this is cosinus of U, sinus of U, V. So the image sigma U that we will call V, this is open in C because it is the intersection with C of the open set X, Y, Z in R3 such that X is different from minus 1. This map is injective, and what is its inverse? So the inverse will be denoted by sigma inverse, and we will show that it is smooth so it points of V plus, which is a set of points having coordinates x, y, z in V with x positive. The inverse of sigma is given by this formula. The inverse of the function tangent evaluated at y over x, comma z. This is clearly smooth because it extends to, so let's write it is smooth because it extends to the smooth function defined by the same formula. On the set, on the open set, x, y, z in R3 such that x is positive. So we proved the smoothness of the inverse of sigma only on V plus. As an exercise, please try to prove the smoothness of sigma inverse at other points of V. So this proves that sigma is a diffeomorphism and sigma is a surface patch. Now, this surface patch here, unfortunately I erased, but the surface patch sigma covers all the points of C such that the first coordinate is not equal to -1. So now we have to take care of the points whose first coordinate is exactly -1. So the points of C at which x is equal -1 can be covered by using another surface patch. Of another surface patch. Let's use the map mu defined on minus pi times r with values in C defined by the following formula. Cosinus of u plus pi sinus of u plus pi comma v. You can prove this is a surface patch using the same arguments we used for sigma. And I want to make a remark. If you look at this function, you will observe that mu is obtained from sigma by composing with it a rotation by pi about the z-axis In fact, here you have that the third coordinate is fixed. Only the first two change. How do they change? Instead of cosinus of u, you have cosinus of u plus pi. And instead of sinus of u, you have sinus of u plus pi. This is the effect of the composition with a rotation by pi about the z-axis. Okay, so this is the end of the proof of the fact that C is a regular surface. So we found two surface patches whose images cover all of the points of the cylinder C. So this implies C is a regular surface. Now, do you remember proposition 3.21? Proposition 3.21 says that if you have a regular surface, then if sigma is a surface patch, d sigma q has rank 2. Here we have also one surface patch denoted by mu. So this proposition says also that d mu q has rank 2. We want to check it directly without using this proposition. So sigma was a map defined by this function, cosinus of u, sinus of u, v. Consequently, if q in u is a point of coordinate uv, then what is d sigma q? D sigma q is dx du at q, where x is this function, dx dv at q, dy du at q, where y is this function, dy dv at q, and then it remains dz du q, dz dv q, where z is this function. If you make computations, you will find minus sinus of u 0, cosinus of u 0, 0, 1. So this is a matrix of rank 2. any u, v in u. In fact, minus sinus of u cosinus of u 0, and this is of course sigma uq, that is the partial derivative of sigma with respect to u, and sigma vq equal to 0, 0, 1 are clearly linearly independent. Okay, so I think for today that's all. See you next week. Thank you for your attention.